My name is Elliot Slaughter, and today I'm going to talk about Pygion, a flexible, scalable interface for task-based parallelism with Python. At Slack, we have a machine called LCLS, which is essentially a giant X-ray laser. At LCLS, what we do is we basically take samples of different kinds, things like proteins, viruses, molecules of whatever kind, crystals, and you can image these things by essentially taking them, you put them in the machine, you shoot them with X-rays, and then you take images of the diffraction patterns that you get as a result when the X-rays bounce off. And so by basically taking a bunch of these images, you can run some sort of a reconstruction algorithm to determine the original electron density of whatever it is that you're taking a picture of. So this essentially turns into a data analysis problem. One of the things about LCLS is that because the time on this machine is so incredibly scarce, the experiments are very high stakes. And so that means there's a big push to do novel science in every single experiment. That means that the data analysis also becomes novel in every single experiment. And because of this novelty and this sort of uncertainty of doing things that are new, what people end up doing is that they write, debug, and execute their code on the fly. This is during the experiment itself. So typically what you'll do is you'll do a run for about 15 minutes. You'll stop, you'll collect your data, you'll do your data analysis as quickly as possible, and then you'll use that to make some sort of a decision. Maybe you'll tweak the experiment, maybe you'll tweak the data analysis, and then you'll go again, right? And you're trying to collect as much data as possible with as much quality as possible in the time frame that you have, and you have a very limited amount of time to get your data before your time runs out. And so the thing about this environment is the users that we have come from a variety. There's a spectrum of experience that we deal with. Some people are very familiar with the high performance tools, but a large number of people who we work with are not experts. They're not formally trained in computer science. They're not necessarily familiar with C++. They're very infrequently familiar with MPI. They may not be familiar with the programming environments. And so we need to deal with people with a variety of levels of experience. And we shouldn't demand that they spend time learning the performance tools before they can be productive, right? They have a very short amount of time to be productive on these machines. They frequently come in late at night or early in the morning, and they need to be productive right away, right? We can't demand that they go learn some programming language first. And so part of the thing that complicates this problem is that the machine is also being upgraded. So in the future, in just a couple of years, we're going to be generating substantially more data, eventually up to 100 gigabytes of data a second. So today, you can run these analyses on your laptop. In the future, that's not going to work. You're going to have to use a supercomputer. And so the question we've been asking is, how can users productively and performantly program these machines to do their data analysis? So we have a large investment in task-based programming models in our group, and so we think this is a promising direction for this problem. And the thing that's really great about task-based models is that they provide sequential semantics. So you write out your code as a series of tasks, and those tasks appear to execute in sequential order. And so the user doesn't have to think about the parallelism. The parallelism is all discovered behind the scenes. The system determines how to execute the series of tasks. And one of the recent advancements has made the scalability particularly effective for these models. And in fact, there's actually going to be an SC talk on this later on in the main conference. But there's this question of how do you program them, right? How do you program these systems? So when we started, we presented a system called Legion, and we were programming it in C++. And that was great as far as it went, but the thing about this model is it has a large, fairly complicated API, which honestly makes it fairly error-prone. It's great for experts who know exactly what they're doing, but for these users who are coming up to speed very quickly, this isn't the best approach for them. So a number of years later, we developed a programming language called Regent, which is essentially a language for the Legion programming model. So it's better because it provides dedicated abstractions for a lot of the things in the Legion programming model, tasks and other sorts of things. But it's still a static language. And so it's really not the right fit for these kinds of users, particularly when they come in their experience with more dynamic languages. And so what we asked was, well, can we provide an interface for these sorts of models in Python? And what we found is that the answer is yes, we can actually provide an efficient, intuitive interface for these task-based models in Python. So you might be thinking, wait, Python? Performance? Are you sure these things go together? Well, actually they do, and let me explain. So there are two things you need to understand. The first is that when you're thinking about a task-based program, you should separate it into two parts. There's the control code, which is the part that is launching tasks, and then there's the kernel code, which is the part that's executing the inner loops in your program. So control code is not on the critical path. Because tasks execute asynchronously, it actually, the control code can execute independently from the bodies of the tasks themselves. And what that means is that what really matters for performance is the average rate that you're executing tasks. So as long as you can stay ahead of the execution, so as long as the rate that you are launching tasks is greater than the rate that those tasks are executing, then performance will be good. The second thing to understand is that there are a variety of optimizations that matter, which we have in the past. We have done those with static analysis in the Regent programming language, so we know that these are important. So one of the insights that we had when we were doing this work was that we can use dynamic analysis in Python based on the program state to recover these optimizations on the fly. And what we found is that out of 7 optimizations that were originally reported in the Regent paper, 5 of those work with dynamic analysis in our Pygion interface. 1 was made irrelevant by unrelated changes in the runtime, and only 1 optimization was unable to be implemented. And so the bottom line is, in our experiments that we've done with this Pygion interface, we have been able to achieve within 3% of the original Regent optimized programs at all node counts, from 1 all the way up to 512 nodes. This is a productive and efficient way to write these programs for supercomputers. So I'm going to talk a little bit about the Pygion programming model, and then after that I'll talk briefly about the optimizations. So in Pygion, typically what you want to do is you want to start by creating some data, and how we do that in Pygion is with something called a region. A region is essentially a table. You can think of it as being like a database table or similar to a pandas data frame, and it has some rows and some set of columns. The rows are identified with keys. These can be potentially multi-dimensional, but for simplicity I'm just showing a 1D set of keys here. And then you have some set of fields. So here we've got X and Y, which are both floats, but you could make these whatever you want. It could be temperature, pressure, chemical concentrations, position, velocity, acceleration, whatever you want. And so this is an extremely flexible and expressive data structure. And then typically what you want to do, because we're doing distributed execution, you want to partition your data structures into pieces that you're going to access in your tasks. And so in this case, we've just used the equal partition operator, which takes this region and divides it into 2 pieces. But we've actually got a language of these partition operators that is extremely expressive, and you can do all sorts of things. For halo exchanges, structured, unstructured meshes, I mean, we have a very expressive language where you can describe exactly which data you need to access. And then typically, once you've created your data, then you're going to want to run some tasks on it. So the way you can do this is you can write a function. This is just standard NumPy code. If you're familiar with NumPy, this is exactly what you'd expect. Just showing Saxby is a very simple example, but of course you can do more complicated things. And then because we've partitioned the data, then we're going to run Saxby on each of the pieces of that data. And this is actually a valid program. It's actually not a parallel program, it's a sequential program because we haven't added any tasks yet, but it is a valid program. Now, how do you add parallelism? You add parallelism by marking functions as tasks. So this annotation task says that Saxby is a function that is eligible to be executed in parallel. And there is one more thing that we need to do here, which is mark the privileges on the data that Saxby is using. So this says that we are going to write the field Y of the region S, and we're going to read the field X in that region. And basically by using the privileges, the partitions, and the sequential execution order, the system is going to do a dependence analysis that determine the order that it can execute these tasks. So to see how that happens, I've made a slightly more complicated code example. So one thing to notice here is that we now have two partitions of the region S, P and Q. So partitions are views onto the data. They are not copies. And so one of the things that the model is doing for you is when you access a partition, it is automatically updated to reflect all of the other updates to partitions that may be overlapping with the data that you're accessing. And then I've gone and I've written a little time step loop with two tasks. And it doesn't matter exactly what the tasks are. The only thing that matters for the purpose of this demonstration is that we have two tasks and they access different partitions. And so let's see what happens when we execute this code. So we're going to start at the top of the time step loop. And as we walk down the code, we're just running it sequentially, exactly like you'd expect for a standard Python code. When you hit a task call, the runtime is going to record that you are executing a task. So we're recording that we access our executing Saxby P0 here. And then as we go back around the loop, we're going to execute Saxby P1. And the thing to notice here is that P0 and P1 do not overlap. They're what we call disjoint regions. And the reason why we know that is because we use the equal operator, those pieces are guaranteed not to overlap. And so we are guaranteed to be able to execute on them in parallel. These are parallel tasks. As we continue executing, we're going to get to the first step task here. And the thing here is that Q0 overlaps with P0. And that means that the first step task is going to depend on Saxby P0. As we continue executing, every task that we hit, we're going to record the dependencies based on what data overlaps with previous tasks that have executed. So Q1 overlaps with P0 and P1, and so that step task is going to have two dependencies, and Q2 overlaps just with P1, and so that third step task is only going to have one dependency. And as we continue executing, we just continue building this dependence graph, which tells us the structure of the parallelism that we have in this program. And in this way, we're recovering basically a description of the program, but the great thing is it's all automatic. The user just had to write this sequential code. They wrote the tasks, they said what order the tasks executed, and the system recovers the parallelism. So just so that you can appreciate what this interface is doing for you, here is a code comparison with Pygion on the left-hand side and C++ on the right-hand side. And you can see that the C++ is clearly quite a bit longer here. But the difference between these codes is actually more than just your typical difference between Python and C++. What's going on here is more that Pygion is a higher level interface than the Legion C++ interface. There are features that have been removed in Pygion that you don't need to think about, and Pygion is automatically filling in those details for you, and that's why the code is so much shorter. And so here's a summary of the features that have been removed in Pygion that are automatically dealt with for you. Unfortunately, because of time constraints, I'm not able to go into details, but please see the paper. There are lots of details on exactly what's being done for you. And then we also have a number of optimizations in Pygion. These are optimizations that we noted when we built the Regent programming language were very important for performance. And the great thing about Pygion is that we have discovered that using dynamic analysis, we can recover most of those optimizations. So out of 7 of the optimizations in the original Regent paper, we were able to implement 5 in Pygion using dynamic analysis. 1 was made irrelevant, and then 1 was not able to be implemented. Here's the list of features. Again, unfortunately, I do not have time to discuss all of these in detail. The details are all in the paper, and there is one additional optimization that I will describe briefly at the end. But for the moment, what I'm going to do is I'm going to dive a little bit more into this index launch optimization so that you can see how one of these optimizations work in the language. So typically what you do in Pygion is you write code that looks like this. You've created your regions, you partitioned them into pieces, and then you want to launch tasks on those pieces, right? So it is extremely typical to write loops that look like this. Now the problem with this approach is that you spend O of n time enumerating the tasks, running this loop in Python, and then you spend O of n time in the C++ runtime trying to analyze those tasks to find the parallelism between those. And that sort of inherently limits the scalability that you can achieve with this approach. An alternative, which we provide, is called an index launch. We also call it a constant time launch, is this alternative form where you've basically made the loop implicit, right? So what we're saying here is we're going to run 2 tasks of SaxP, and each thing is going to get the ith piece of P. So this ID thing here is an implicit loop variable that says each element of SaxP, when we execute it, is going to get the ith element. And the great thing about this constant time launch approach is that it is constant time, as it says in the name. It is O of 1 time to enumerate the tasks, it is O of 1 time to analyze the tasks, and that gives us much superior scalability. It's just a little bit more detail about how that works. When you run this code, you can think about it as essentially being desugared in this way. This is not literal Python code, but it's sort of showing you what's happening behind the scenes. So this PID thing, ID is essentially a symbolic variable that represents the loop index, right? And so what we're storing when we're executing this Python code is actually an AST that describes this expression that we're going to execute. Then we launch the task using this launch API. And then on the caller side, which is not being shown here, then you basically execute that AST to recover the actual value that you wanted to pass into that task. And so by describing these expressions as ASTs, we're able to basically reduce the time that needs to be spent on the caller side to constant time. So we did an evaluation on a Cray machine called Pygion, which has NVIDIA, Tesla, Pascal GPUs, and we took 3 already optimized applications written in Regent, and we weak scaled them from 1 node up to 512. And in order to make things as apples to apples as possible, we used the original optimized GPU kernels from those applications. So the only thing that is changing here is the use of Regent versus Pygion. And the thing to notice here is that we achieved within 3% of the performance of Regent at all node counts. And so what we're showing here is the control code, essentially the Python, was fast enough to keep up with the executions of these programs. One last thing I'll leave you with. We've been using this actually at Slack to develop some real applications. So Minifel is a proxy application developed as part of an ECP project that we have here at Slack called XFL. Minifel is written entirely in Pygion. It is essentially a data analysis framework for certain kinds of single particle analysis problems. And the great thing about Minifel is that it has been written entirely by the domain scientists with fairly minimal help from us. And so what we've been able to do is show that domain scientists are actually able to use this interface to productively program these machines. And so this sort of indicates that this is a promising direction for this project to achieve productive performance. We are very grateful to ECP for our funding, and with that, I'm happy to take any questions.